All right, we are going over the second half of the semester 1 review packet. So first it's asking us to write electron configurations. So let's take a quick peek at this periodic table again. I want to remind you that over here we've got the S block, all of the orange. The blue is the D block. The red is the P block. And the pink at the bottom is the F block. I also want to point out, I wish they were on here, but over here on the left side, this is period 1, second row is period 2, period 3, can't write on the screen, period 4, 5, 6, 7. And you'll notice that matches out the numbers out front for the S block and the P block, but not the D block. It always skips down. This is the 4th period, but this is 3D. This is the 5th period, but it's 4D. Okay, that's important. So the first thing it asked us to write an electron configuration for is carbon. So carbon's number 6 right here in group 4A. You always start at hydrogen. You go until you hit a double line. There should actually be a double line on this far right side too. Okay, so you get to helium and you write down 1s2. Then you go like you're reading a book, left to right. Then you get here to this double line, 2s2. Keep going until you get to carbon. That's in the 2p, 1, 2 over, so 2p6. That's where the electrons live. Okay, so let's go back here and write this out. 1s2, 2s2, 2p2. So if we were to draw a little picture of carbon, here's the nucleus. The first shell has 2 electrons because of the number 1, that's shell 1. And the 2 here is 2 electrons. And then the second shell has 2 electrons in an S and 2 electrons in a P, so 4 electrons. So 6 total, 4 in the outer shell. Okay, bromine is the same sort of a thing, it's just longer. So bromines is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember, it skips down 1. 4p, and it's 5 over. Now, it's a lot easier to write the noble gas electron configuration. So the way that you do that is for fluorine, for example, you look at what was the last noble gas before fluorine. Reminder, group 8A right here is the noble gases. So you get to put the last noble gas in brackets. So helium in brackets, and then you just continue on as usual till you get to fluorine. So for tin, number 50, the last noble gas before tin is krypton. Okay, so these will turn out like this. For fluorine, helium in brackets, and then 2s2, 2p5. And for tin, it'll be krypton in brackets, 5s2, 4d10, 5p2. 37. Identify the element whose last electron enters and fills the 4s. So check it out. In the 4s, calcium is the last element there, so that should be calcium. What enters but does not fill the 4s? So the one before it is potassium. Which is the first to enter the 2p? Check it out. Number 5, boron, is the first to enter the 2p. What's the next to last to enter the 4p? So here's 4p, krypton's the last one, so the next to last would be bromine. And what's the second to enter the 4d? Here's 4d, yttrium is first, zirconium, Zr, is the second one. Indicate the block that in which each of these elements is found. So you just need to look on here, for example, Mn is in the D block. Okay? And if you look where phosphorus is, it's in the P block. Francium is in the S block. Nickel, also a transition metal. Arsenic in the P block. And uranium is at the bottom in the F block. Don't worry about writing configurations that include things with the F block. Alright, then it says, use these configurations to figure out what family they're in. So you just look at the last little bit, 3p6, find 3p6, it's argon. Argon's in group 8A, That's the noble gases. Okay, I'm going to write down what it is too. Letter B, that is fluorine. Fluorine is in group 7A. Those are called the halogens. 3s2 ends on magnesium. Those are called the alkaline earth metals. Letter D, this one ends in 3d5. That's manganese. That's a transition metal. Number 40, explain the difference between ground state and excited state. So ground state is when an electron is closer to the nucleus. The excited state is when that electron jumps up to a higher energy shell. That's more unstable. 41, what are bright line spectra? How are they formed? What determines the color of light? What colors of light are high energy and what are low energy? All right, so bright line spectra are basically fingerprints of elements. You might remember these. We were looking through the spectroscopes at the different gases, and for each one we saw different bands of color when that prism broke the light down. So these form when electrons get excited by electricity or by heat, and when they jump up, that's unstable. So when they fall back down, they release a photon of light. If it was a really small fall, that's low energy. So low energy is from a small fall, and that would emit a long wavelength of light like the color red. Okay, now if it was a really big jump, I'm going to add more shells. Whoa, it jumps way out here and falls all the way back down. That's going to be a really high energy color. So high energy equals a big fall, and that would be a color like violet. Explain how a sample containing one element like helium can produce many different colors of light. Well, when you've got helium, it's got 2 electrons, and those electrons can end up jumping to different energy levels and falling back down. So when you've got lots of atoms of helium and lots of electrons are jumping to different levels, you're going to give off different colors of light. Okay, so many atoms equals many electrons jumping and falling and releasing different photons, different colors. All right, nuclear chemistry, my favorite. Compare and contrast nuclear fission and fusion. Both release a ton of energy. I think of fission like there's 2 S's and you got to split them apart. Fission is when a heavy nucleus, like uranium, for example, is split. Okay, provide an example of each. So this is what they're doing in power plants. Also, the atomic bomb. Those both involve a splitting of nuclei. That energy that was holding the nucleus together is now released because it's not needed to hold the nucleus anymore. So when you split it, you can use that energy for things like a bomb, which sounds pretty destructive, or clean energy in a power plant. All right, let's talk about fusion. Fusion is when 2 or more small nuclei combine. This also releases a lot of energy. This is what's happening in the sun and the stars. Atoms are fusing together to form new atoms. So in the sun, hydrogen atoms are fusing together to form helium. And you can tell from the sun how much energy that releases. All right, complete the table. alpha and beta. So this is just something you should have memorized. Alpha particles have a positive charge, a mass of 4. When an alpha particle is released from an atom, the atomic number goes down by 2 and the mass goes down by 4. That's because an alpha particle actually is a helium nucleus without the electrons. It's made of 2 protons and 2 neutrons. Beta particles have a negative charge. They have no mass. The atomic number goes up by 1 during beta decay, and the mass is unaffected. All right, let's look at some examples here. If I can scroll down, page down, try it this way. Oh, it's gonna not respond for a second here. There we go. Come back. I might have to start a new video if this doesn't come back here for a second. 5, 4, 3, 2, 1. Stupid computer.